In today's video, we're going to go over several different ways to depict alkanes and their conformations. As you're drawing alkanes, it's important to remember that your drawing is depicting a three-dimensional structure that really exists. And so you want to make sure that you consider you're maintaining appropriate bond angles. And so these bond angles for an alkane we've talked about are 109.5 degrees. And you want to do your best to maintain that as much as possible. So this is the best way to think about drawing that in 3 dimensions. Another way that you might see that is acceptable but maybe not the best is sometimes known as a bow tie structure, where you have two hydrogens coming out at you and two going back into the page. This structure is acceptable, but generally not the best. Some common mistakes that I see. The first one is having all the bonds coming out on one side of the page. Hopefully you can see that none of those bond angles work, and it looks almost like there's a strong wind coming from the right-hand side of the page and blowing all those hydrogens to one side of the molecule. That's incorrect, and we don't want to draw it that way. The last one that I see a fair amount is this. Where the wedged and dashed lines are split between by another hydrogen. The wedge and dash line should always be right beside each other. You never want to see it split. And so this is also a bad representation of an alkane. Because rotation can happen across single bonds, ethane exists in several conformations. And chemists have a variety of different ways to depict those, and so I'm going to go over a few of those. The first one is a perspective drawing, and that's the wedges and dashes that we've seen before. And so ethane can exist in the eclipsed conformation. In the eclipsed conformation, the hydrogens on each carbon all line up with one another. If you looked down the CC bond, all these hydrogens would be in the same plane. And so this is known as the eclipsed conformation. If you were to rotate this bond 180 degrees, I'm going to make that hydrogen a green hydrogen so we can see this. I'm going to keep the carbon on the left in the same orientation. And rotate that green hydrogen down. And that's going to move the other two hydrogens up to the top. This structure is known as a staggered conformation. Hopefully you can see that this hydrogen and this hydrogen are 180 degrees apart and they don't line up. Another way we might depict this is known as a sawhorse structure. And in this scenario, these three hydrogens represent the three hydrogens on the carbon on the left-hand side of this molecule. And I'm going to draw back to my second carbon, where I have a green hydrogen sticking up and the two hydrogens sticking down, like so. So this first representation we're calling a perspective drawing. This set of drawings are known as sawhorse structures. If we look at the staggered conformation, the front carbon is going to be the same. The back carbon now has a green hydrogen going down. And two blue hydrogens going up. So that might be slightly easier to see the staggered structure of this, but I think the easiest way to see this conformation is using what's called a Newman projection. So a Newman projection, we are going to look down this carbon-carbon bond from the right-hand side of the page. And so this front carbon looks like this. And we draw that circle to indicate that's the bond we're looking behind. And this is the carbon in front. And the carbon in the back, we're going to start our substituents at the top of the circle to distinguish them. And so this is the eclipsed conformation where the dihedral angle, or the angle here, is 0 degrees. The staggered conformation rotates about that bond 180 degrees, so I'm going to leave the front carbon the same. But the back carbon now has a green hydrogen going straight down. And the other two hydrogens split this. And so now the dihedral angle between the top blue hydrogen and the green hydrogen is 180 degrees. The conformations of a molecule often do not have the same energy, and so as you rotate around that carbon-carbon bond, you increase and decrease in potential energy. So we can generate a potential energy curve with respect to the dihedral angle across the bond that we're rotating around. So I want to start with the the staggered conformation of ethane. And I'm going to give myself a red hydrogen at the top. And a green hydrogen at the bottom on the back carbon, so that we can illustrate these dihedral angles. So right now, the red and green hydrogen are 180 degrees apart. That's the staggered conformation. If I were to rotate that molecule 60 degrees, and I'm going to rotate the back 60 degrees to the right, I would wind up with something like this. Where now the red hydrogen and the green hydrogen are 120 degrees apart. Now I'm going to keep going in 60-degree increments. Now I'm back to a staggered conformation. But now the red and green hydrogens are only 60 degrees apart. And I can keep going all the way to 0 degrees. If I do the same thing rotating the bottom hydrogen or the green hydrogen to the left, I can fill in 240, 300, and 360 degrees. If we consider the potential energy of both of these, or of these conformations, the staggered conformation is going to be the lowest energy because there's the most space between the hydrogens. Remember that these carbon-hydrogen bonds, there's a lot of electron density in them, and so we want to get them as far apart away from one another as possible because electrons repel each other. And so the staggered conformation is the lowest energy. So I'm going to put a mark at this 180 degrees where they're the farthest apart to say that's the lowest energy. And hopefully it's clear that all of the staggered conformations are the same because there's only hydrogens in here. And so I'm going to go through for each staggered conformation and put a line representing a low energy pathway or spot in this curve. And the eclipse conformations are going to be higher energy. And again, all of the eclipse conformations have the same energy because they're eclipsing hydrogens in each case. And as you rotate around that axis, you generate this sinusoidal-like curve that goes up and down as you rotate around. And so when we say we have two limiting conformations, we're talking about the staggered conformation and the eclipsed conformation as the lowest energy for the staggered and the highest energy for the eclipsed conformations of ethane. As you rotate around this bond, the difference in energy from the staggered conformation to the eclipsed conformation is about 3 kcals or kilocalories per mole. Since each eclipsed conformation has 1, 2, 3 hydrogens that are eclipsed, an eclipsed hydrogen interaction is worth about 1 kcal per mole. Or another way to say that is anytime you have an eclipsed hydrogen, that adds a kcal per mole greater than the lowest energy conformation that's possible. For ethane, that 3 kcals per mole energy barrier between the eclipsed conformation and the staggered conformation is a really small energy barrier. And so At room temperature, ethane is constantly spinning around, entering all of these conformations at any given moment. Let's make this a little more complicated and think about the conformations possible for propane, or a 3-carbon molecule like this. And I'm going to look down the C1-C2 bond when I think about my Newman projection. And so carbon 1 is that front carbon, and carbon 2 is the back carbon. Carbon 3 is attached to carbon 2, so I'm going to go ahead and write my CH3. So this is carbon 3 here, and this is carbon 3 in my drawing up there. I'm going to give myself a red hydrogen on carbon 1 just so I can keep track of where it is. And I'm going to fill in the rest of the molecule. So this is the staggered conformation of propane. If I rotate that molecule 180 degrees, or I rotate that back carbon 180 degrees, I generate a structure that looks like this. My red hydrogen is still up top, but now my CH3 is eclipsed with that red hydrogen, like this. So this is the eclipsed conformation. When we're thinking about the energy costs of being staggered versus eclipsed, the size of the substituents matters. So this methyl group is bigger than a proton, and so this costs propane about 3.3 kcals per mole to be eclipsed versus staggered. If you recall in the last slide for ethane, we noticed that each hydrogen being eclipsed was worth about 1 kcal per mole. And so in propane, we have two hydrogen eclipse interactions that are worth 1 kcal per mole each. And the total is 3.3. So what that tells me is that one hydrogen CH3 eclipse interaction costs about 1.3 kcals per mole in energy. That's going to wrap up today's video. See if you can complete the potential energy curve versus dihedral angle for propane, and we'll pick up there next time we meet in class.